Hello, welcome back to Fluid Dynamics 7th chapter. We now want to have a close look at momentum and force balances. Um, First, for example, if you want to build up a windmill or a turbine or any other fluid energy machine, what is most important for you? You have to estimate before you start the design of your windmill. You have to estimate how much force can you get from the fluid, how much energy can you get from the fluid. And um, so at first we have to introduce a so-called momentum law or momentum balance. And the momentum is defined as mass times velocity. So you have the mass of the fluid, you can calculate it by the volume, and then you have a velocity, and this gives you a potential momentum. And on the other side, we want to calculate the forces on the plates to estimate the power of the fluid energy machine. And to calculate the forces, you have to make a derivation of the momentum, and this derivation of the momentum gives you the forces on the surface of the plates here. So how can we calculate forces and momentums from fluid flows? That's now our topic. Of course, as you have seen, the geometry of such a windmill is really complicated and complex, and also we spend always a lot of time on the calculation of the geometries and the calculation of the areas. This is a rather tough job. If you have a normal simple plate, it's not so difficult, but if the geometry is more complicated, you can imagine that the forces and the momentum on this complicated geometries is much more complicated. And so in general, to design a new fluid energy machine, to design a new windmill or to design a new turbine, it is essential to use CFD, computational fluid dynamics. We use the program ANSYS CFX in general to model such complicated geometries, and then we can calculate pressure fields around the windmill, or we can calculate streamlines and velocity fields around the windmills. But this is now a bit far away, this step. Let's concentrate on more easy geometries first. Because if you want to calculate such complicated geometries, you have to spend a lot of time on defining the geometry, on modeling your windmill or your airplane or your car, and it's also really time consuming to do the simulations. And here's an example of a big simulation center, or let's call it high performance computing center in Stuttgart. And you see some examples, complicated flow examples around difficult geometries. But before we come to these difficult examples, we want to have a look at more easy examples. And the easiest fluid flow calculations, of course, is not the calculation of a compressible media like air. More easy is calculation of an incompressible media like water. And we don't want to make our geometry so complicated. We just want to have a look at an inclined plane where a water jet hits a plane. Here you see a sketch from this simple example. You have your plane, your inclined plane. You can twist it a bit. You can get different angles here. And then we have our water jet. The water jet hits the plane, and one part of the water goes upwards, one part of the water goes downwards along the plane, and we have a momentum, and to calculate the forces on the plate, because it could be necessary to fix it at a wall, for example, then we have to know the forces that act on this plate, otherwise we will push it away. So to calculate the forces, we have to make a force balance here, and the forces, if you calculate them, you need to know the velocity of the fluid, you need the area of the jet, and then you can calculate the momentum, and the derivation of the momentum is the force. So we make a force balance, and to calculate a force balance we use a momentum balance, and we need to define special control volumes. For example, at this inclined plate we have to define the area where the jet hits the surface, and also we have to take into account the angle of the inclined plate, because you can imagine if you hit the plate with a 90-degree angle, you get the full force. But if you incline the plate more or less, you get less forces and less momentum. So first we have a look at the fluid flow, at the jet, and to calculate velocities and pressures, we use a so-called Bernoulli equation, and the Bernoulli equation is in some way energy balance, and then we can calculate the pressures, that we can take into account the velocities, and of course we neglect the part for the height, and so we can calculate the different fluid velocities. And if we now come back to our plate, we know the angle of the inclination, and we know the jet and the direction of the jet, and now we can take into account every part of the momentum in every direction. So if we have a force in x direction, and we take the cosinus of the inclination angle and add the three different derivations of the momentum. So we have one momentum part here that comes from the front, that hits the plate, but we have two momentums that can be for the jet that goes to every side. So we have to subtract the part from the jets to the side, is this part, and we subtract it from the part of the jet, and additionally to our momentum, to our velocity, we have to take into account, depending on Bernoulli equation, the part of the pressure. And the part of the pressure and force is always pressure times area, so we have to take into account the inclination of the area, the angle times the area times the pressure difference. And for forces in y direction, we have to do the same momentum balance again. And then we can calculate, depending on this terms, the forces in x and y direction, and then we get the forces on our plate. Okay. Let's have a look at the next example. And the next example is not a plate, but it is really similar to our plate example, and it is a 90-degree pipe element. That's also an important calculation for fluid dynamics. In many cases we have pipes, we have water pipes or gas pipes, and if water or gas flows with high velocity through this pipe, we get a force on the walls, and we need to know how to calculate the forces on the walls. And if you have our pipe, we have here an area and an angle, and we can calculate our mass flow, we can calculate our velocities, and then we multiply the mass flow with the velocities, and then we have the derivation of the momentum, and this again is a force in the x and the force in the y direction. And to calculate a resulting force depending on the forces in x and y direction, we need our Pythagoras law, so that's the square root of the squares of both forces, depending on vector calculation. Okay, here again is the same picture. We have our pipe, we have our 90-degree pipe. The water enters from the left with a defined velocity and a defined momentum, and then it goes through the pipe, and we can now calculate many different small forces, but we take one general force. So we say our balance, we want to calculate our balance in the middle, so we have to take into account both forces, make a balance, and then we get the forces on the wall of the pipe. Okay, and here is the definition. Again, we get a force in x direction, we get a force in y direction, we take into account the angles, we have to take into account, based on Bernoulli's law, again the momentum times cosinus alpha for the force in x direction, and sinus alpha depending on the force in y direction. Okay, let's have a look at a more complicated example. In general, it is more or less the same problem. We have a turbine. Here we have a Pellet turbine, and it runs with water. You can see an example of this kind of Pellet turbine. I made this movie by myself. If you follow the link if you refer to the slides, you follow the link, or you scan the QR code with your mobile, then you can get to this YouTube video where you see how it works. And in general, you have a nozzle and you have a jet. The jet has a defined area, the jet of water has a defined velocity, and now if the jet hits these buckets of the turbine wheel, you can calculate the forces acting on this bucket. So I think if you want to know in detail how it works, please watch the movie. I think it's a simple principle. And how can we calculate the forces and the momentum on the bucket? Again, we take the velocity and we take the mass flow, and then we calculate the forces. So here you see a more complicated example of this Pellet turbine. It's a water jet turbine. You see the buckets, more or less they are the same as in the slide before, but you can, if you look closely at the slides, you can see the buckets are divided in two different pockets, and this is to get a more defined jet and a more defined momentum balance. Okay. Before we look closely at this complicated geometry, we want to look at the power on the shaft and the power without losses. And this is our efficiency. And the efficiency of a water turbine in general is the derivation of the work on the shaft, so the power that acts on the shaft, divided by the power of the water. Yeah? And this power of the water is defined by the potential energy times volume flow. So, and to get the power on the shaft, you need the momentum at the shaft and multiply it with a omega value to get the power acting on the shaft. Okay, here you see again a sketch of our Pelton turbine, and if you have a pump or a turbine, you always try to calculate the specific energy. If you want to design your turbine, at first you have to estimate the specific energy you want to get from your fluid, and then you can choose with this specific energy a special turbine. For example, here our specific energy is defined as gravity constant times height difference. And we can, at this Pelton turbine, we can get really high height differences, about 1000 meters, and you can define your pressure difference, you divide it by the density, and then you add a term of the specific energy that is based on the velocities. Okay, here we come back to our buckets, to our wheel. We see our turbine Pelton type wheel. We have our buckets, we have our jet and the volume flow, and now we want to calculate the forces acting on such a bucket. And to calculate it, we have to know that we have this splitter. We have this. The bucket is divided in two different pockets, and inside the bucket there's this so-called splitter, and the splitter is designed. It is not a flat or inclined plane. If it's a normal plane, it's much more easy. But if the splitter is divided in two different pockets, you get a jet in every direction. Here you see it more detailed. We have our water jet. That's a picture. Maybe if you can't see it so good on YouTube, please go to the slides. You have our jet. It hits the bucket and the splitter of the bucket in the middle, and then the splitter divides the jet in two different small jets, and he changes the direction of the water, and then we have an additional momentum in the other direction. So that's designed to get the best, the highest momentum out of your water jet. Okay, here you see again the splitter geometry, and more or less the angle is not 180 degrees. This would be the best splitter design, but it is a bit less because the jet that exits the splitter area should not hit the bucket that is before our bucket where the forces act. So you can't use totally 100% of the energy. Okay, here's again the momentum balance and external forces. Here we see our forces again, and now we have an object in the middle, and here it is the same. If we want to make a balance of all the forces, we have to sum up the derivation of the momentums. We have to sum up the pressure forces and all the other forces, for example gravity forces, and we have to make a balance. So altogether it has to be 0, and then we can estimate the single amounts of the forces. Okay, here you see it again. You have our type. The fluid enters the channel, the fluid exits this channel, and here again it's also same picture again. The fluid enters the channel, it exits the channel, and we can calculate our momentum based on the mass of the water times the velocity. Okay, and here it's the same picture. We have our shaft, and now it's a special formulation for the efficiency of the Pelton turbine. We have to take into account that the water will not exit the bucket in a 180-degree angle. This will be an optimum angle. The fluid will exit it in a smaller angle, because we don't want to hit with the jet that exits the bucket the other bucket here in the front. So we can't use the full energy. We will always have our efficiency will always be a bit below 1 or below 100%. And at the exit, one of the last slides, if we now can calculate the forces on our blades of the turbine, and then we can calculate the forces on the shaft, and based on this we can also calculate the power, and the power is the mass flow times the specific energy times our efficiency of the turbine, and then we can estimate the power we get from the fluid.